My name is Javier Camara, and in this video I'm going to present explaining architectural design trade-off spaces, a machine learning approach. Nowadays, architecting modern software-intensive systems requires exploring design spaces that are often poorly understood due to the increasing complexity and range of design choices that have to be made, as well as their potential interactions. There are many existing approaches that help to automate the search for good architectures and that rely on a variety of techniques to enable architects to explore how the satisfaction of quality of service requirements varies as the value of design parameters and environment variables change. However, despite being informative, these approaches do not always make clear why and how architectures were selected because they do not explicitly link design decisions and environmental factors to the satisfaction of requirements. They yield vast amounts of data that are not easy to interpret by a human designer, and results include both useful information and noise that obscures the understanding of relations among variables. Architects need tools to help them understand the trade-offs of complex design spaces and guide them to good designs, enabling them to understand which design choices are significant, which choices impact what qualities, and how design choices interact with each other. To illustrate why this is important, let's have a look at a motivating example. The TAS or teleassistance system is a service-based system whose goal is tracking a patient's vital parameters to adapt drug type or dose when needed and taking actions in case of emergency. TAS combines three service types in a workflow that you can see to the right of the slide. When TAS receives a request that includes the vital parameters of a patient, a medical service analyzes the data and replies with instructions to either change the patient's drug type, change the drug dose, or trigger an alarm for first responders in case of emergency. When changing the drug type or dose, TAS notifies a local pharmacy using a drug service, whereas first responders are notified via an alarm service. The functionality of each service type in TAS is provided by multiple third parties that you can see in Table A, with different levels of performance, reliability, and cost. Finding an adequate design for the system entails understanding the trade-off space by selecting the set of system configurations that satisfy structural constraints, behavioral correctness properties, and quality requirements, which can be formulated as a combination of quantitative constraints and optimizations like the ones that can be seen in Table B. There are multiple approaches that automate in one way or another the analysis of architectural trade-offs. In this case, we illustrate the analysis of TAS using one of them that corresponds to our prior work, which enables analyzing quantitative warranties across the design space. The plot on the top shows the minimized cost of configurations for different levels of constraints on response time and reliability. This plot conveys the intuition that higher response times and lower reliability correspond to lower costs, whereas peaks in cost are reached with lowest failure rates and response times. The plot on the bottom is a map that shows which configurations best satisfy design criteria. Although these plots are informative and help architects to understand what specific configurations might work well in a given situation, looking at them does not facilitate understanding what design decisions influence these trade-offs. Answering to what extent improvements on qualities are a function of the choice of a specific service implementation, the topological arrangement of the composition, or the value of configuration parameters, for instance the maximum number of retries when a service fails, is not possible with existing approaches. One of the main challenges in facilitating the understanding of the trade-off space relates to the high dimensionality of the data and how to make it digestible to a human designer. There are too many characteristics of configurations and relations among them to track, and some of them contribute more than others to the variation of quality attributes. For instance, even in the relatively simple system illustrated here, it is unclear if selecting specific services contributes more to system quality variation than workflow configuration parameters like timeout length. Architects need tools and techniques to help them understand the trade-offs of complex design spaces and guide them to good designs, enabling them to answer questions such as why are these trade-offs being made and not others? What are the most important parameters and qualities that are driving the key design decisions? How sensitive to a particular set of decisions is the satisfaction of constraints or the achievement of optimality? And which choices are correlated with others, either positively or negatively. Providing such tool support demands investigating questions such as how can we link architectural design decisions and requirement satisfaction in a way that highlights the most important dependencies among them, and how much can we reduce the complexity of the information presented to the architect while preserving most of the relevant design trade-off information. Our work explores these questions by introducing an approach to enable the explainability of architectural design spaces that addresses the limitations that we have described. The approach employs a dimensionality reduction technique called Principal Component Analysis, or PCA, which is typically employed to compress information in machine learning pipelines, for instance by reducing the number of features provided as input to a neural network classifier, as well as in natural sciences like biology to interpret high-dimensional data. In our case, we combine dimensionality reduction with quantitative verification to facilitate understanding how design decisions contribute to the satisfaction of quantitative requirements across the architectural design space. The inputs to our approach for explaining design trade-offs are a set of legal configurations captured as attribute-annotated graphs, and a set of quantitative metrics that can capture aspects related, for instance, to the energy consumption, timeliness, or safety of configurations. The output of the process is a plot that captures a description of the relations between design and QoS variables. For instance, response time is negatively correlated with reliability, or selection of component X contributes to lower response times and higher cost, as well as their contributions to differences among architectural configurations. The approach consists of 3 stages. Configuration data extraction collects relevant information about the characteristics of architecture configurations. Data extracted includes both topological information, for instance centrality and cardinality measures of nodes corresponding to various architectural types and bindings, and information related to properties of components, connectors, and other parameters. This stage constitutes the core of our approach, and although we only illustrate it intuitively in this video, the process is described in detail in the paper. This figure shows a task configuration and a part of its encoding in the correlations table. The first and second topmost tables show the presence of architectural elements and type cardinalities. In this case, we can observe that the cardinality of all architectural types is 1, except for the connector type, of which we have several instances. The 2 tables at the bottom describe the presence of bindings between components and their betweenness centrality, which is a measure of node importance typically used in graph theory. TAS is built as a service orchestration with a centralized workflow, meaning that all components but the workflow itself will have a betweenness centrality of 0. However, it is worth noting that this is not the case in other architectures, such as the distributed system evaluated in the paper, in addition to TAS, where topological variables have a remarkable impact on QoS variation. In the second stage of the approach, the configuration data produced earlier and the configuration metrics provided as input to the process are aggregated into a single correlations table. Table data is also normalized so that all variables have the same weight in subsequent analysis steps. Finally, PCA is employed to discover how architectural configurations differ and which variables contribute the most to that difference. Moreover, PCA enables us to discriminate whether variables contribute in the same way or in a different way, that is, whether they are positively or negatively correlated, or if instead they are independent from each other. This enables architects to relate response variation, such as QoS metrics and other quantitative properties, to design variables. Datasets resulting from analyzing architectural spaces usually contain a large amount of information. PCA is a statistical projection method that can facilitate understanding that information by finding out in what respect some architectural configurations differ from others and which variables contribute to this difference. Moreover, PCA also enables quantifying the amount of useful information in a dataset, as opposed to noise or meaningless variations. If we consider the data in the correlations table geometrically, we can say that 2 samples, or architectural configurations, are similar if they have close values for most variables, that is, they are in the same region of the space. Considering this, the purpose of PCA is finding the directions in space in which the distance between points is the largest. That is equivalent to finding the linear combinations, called principal components or PCs, of the variables that contribute most to making the configurations different from each other. PCs are computed in an iterative manner, in such a way that the first PC is the one that carries most information, or most explained variance, whereas the second PC will carry the maximum share of the information not taken into account by the previous PC, and so on. In fact, this is one of the characteristics of PCA that makes it appealing as an underlying mechanism to enable the explainability of architectural design trade-off spaces. The interpretation of PCs can be prioritized since the first PCs are known to carry the most information. But let's clarify these concepts by taking a look at an example. The PCA loadings plot of the samples analyzed for TAS displays the first two PCs. These PCs carry plenty of information and explain 83% of the variance of data, with PC1 explaining the most, 68%, and PC2 explaining much less variance. The plot contains two ellipses that indicate how much variance is taken into account. The outer ellipse is the unit circle and indicates 100% explained variance, whereas the inner ellipse indicates 50% of explained variance. Variables that are found between the edges of the two ellipses, and particularly those positioned near the edge of the outer ellipse, are those that are more important to differentiate the configurations. QoS metrics like reliability, cost, and response time are all important to differentiate configurations, with response time being the most relevant one, close to -1 in PC1, which accounts for almost 70% of the overall variability. Reliability and cost are important for PC2, but comparatively have less influence. In addition to teasing out the most important variables, the plot displays the relationships between variables. In the plot, the angle between the vectors that go from the origin of coordinates to a variable point is an approximation of the correlation between the variables. A small angle indicates the variables are positively correlated, and an angle of 90 degrees indicates that the variables are not correlated. An angle close to 180 degrees indicates the variables are negatively correlated. In our example, we can observe that reliability and cost are positively correlated, whereas response time is negatively correlated with both of them. These observations are consistent with the results obtained with our trade-off analysis technique, which show that low response times and high reliability correspond to higher cost. So far, we have been discussing QoS variables, but the loading plot also enables architects to observe the influence of design variables on variability. Here, we can see in the lower right quadrant of the ellipse that some of the most influential variables for PC1 correspond to the presence of a LAMP service instance AS3 in a configuration. We observe that all design variables related to AS3 are positively correlated with reliability and cost, and negatively correlated with response time. This indicates that the selection of AS3 has a remarkable influence on the qualities of the resulting configurations, and is consistent with the fact that the alternative alarm service implementations have considerably higher failure rates and response times than AS3, as well as lower cost per invocation. For our evaluation, we generated the set of architectural configurations and their QoS metrics for TAS and an additional system described in the paper. The analysis of the data showed that in both scenarios there is a remarkable reduction in the amount of information that has to be examined to analyze the trade-off space, which is in the range 80 to 93%. With respect to preserving relevant trade-off information, we observed that the total residual variance ranges between 19 and 25%. Although non-negligible, these are moderate levels of residual variance, especially if we consider them in the context of the drastic dimensionality reduction in the set of explanatory variables. In this paper, we have presented what is, to the best of our knowledge, the first approach that explicitly relates QoS and architectural design variables using dimensionality reduction techniques. Our results show feasibility of the approach and indicate that a remarkable reduction of the amount of information required to explain the main trade-offs of an architectural design space is attainable while the reduction in explained variance remains moderate. Although our approach works well in the case studies presented, PCA works optimally only in the situation where variable correlations are linear or an approximation thereof. Future work will involve exploring alternatives to PCA that enable the analysis of systems with strong nonlinear correlations. Moreover, our approach is currently limited to component and connector static architectures with binary connectors. Our future work will also explore extensions to the catalog of metrics and extraction functions required to enable richer analysis of various styles of architectural representation, including dynamic architectures.